Is it taught on recursion or something? Is it taught on recursion somehow?
No, I don't think we will use this. Not in the word.
What's possible is that low sure. Control L pressing. I think you might just want to press on the slide, and click on the slide, and
Yes.
the focus is on Zoom.
Yeah.
So welcome everyone. It's a pleasure to have Kuldeep Meel as our speaker today. Kuldeep is an associate professor at Georgia Tech and also a faculty member at the University of Toronto, where he's currently on leave. His research interests lie at the intersection of formal methods and artificial intelligence. So Kuldeep has received several awards, including Sigmod Research Highlight Award, ICHKAI 2022, Early Career Spotlight Award, Distinguished Paper Awards in CAB, and was also named AI's 10 to watch in IEEE Intelligent Systems. He's also passionate about teaching and has received university level annual teaching excellence awards. So today he's going to talk about a theory of computing with CAD solvers. So what he will do.
Yeah. Thanks, Shivashit, for hosting me. So this is joint work with Gunjan Kumar, who is a PhD student here. In fact, the last time I gave a talk, Gunjan was a PhD student, and he went on to come do a postdoc with me. So hopefully that trend will continue with this talk as well. So along and a sort of joint work with Saurabh Chakrabarty, who is a faculty member at ISI Kolkata, Deepika Chakrabarty, who is faculty member at NUS, and Remy Delaney, who was my master's student a few years ago. So I work mostly on building solvers and trying to use set solvers in practice. And over the years, we have been implementing these algorithms, which it really means having a GitHub repository. You can download it and run it. And as we develop these algorithms, we have been trying to figure out every time to write a theorem. And in case of writing a theorem, we have been trying to say, well, what are the models we can appeal to? And over the years, we have found that the existing theory isn't fully sufficient. So this is a talk to get more theoretical minded people interested in the problem. So hopefully I'll talk about why, what's limiting about the current theory, and there are some results that we have along the way. And shortly in the talk, the second half of the title of this power of satisfying assignment will become clear. Okay. Since this is kind of a new work, I definitely want you to just pause me and ask questions. Please don't wait until the end. So if we had to propose a new theory or argue that we had to modify the existing theory, it's perhaps a good idea to look at the past, how we came all the way here. And Knut, who is considered the founder of modern analysis of algorithms, argues that why we do algorithm analysis after all. So he gives two reasons. One is that, well, you get to encounter the beauty of mathematical patterns, which is what perhaps attracts a lot of people to theoretical computer science. And the second reason is if you do this theoretical analysis, you come up with an algorithm which has a better complexity, then you also gain practical benefits. Because if you were to implement the algorithm, it would run faster. So how Knut went about analyzing algorithms? It looks very obvious right now, but if you were in early 60s, it wasn't clear because algorithms used to be written in pseudocode where you are trying to figure out what will be the machine instructions. So how do you analyze the complexity of these two pseudocodes? So Knut's idea was that, well, we had to identify for every operation how long it what is cost. We had also come up with some input model, what kind of inputs will be given. And then for a given code, we are going to ask how many times the operation is called. And the runtime will be that sum of the for every operation, the frequency of how often it is called times the cost. And what did this enable us? Well, this allowed us to predict algorithm performance. So if you have an algorithm whose complexity is 5n, then n is some input parameter, then you expect that as n grows, the performance will be linear. And it also allowed us to compare two algorithms. If you have an algorithm that's complexity is 5n versus 10n, then you expect 5n to be better than 10n. Sometimes you just want to compare between n and n squared, so you can forget these constants. Because now we had a measure, it also allowed us to improve. So if you have an algorithm with 5n, you want something better, you hope to get something that looks like, let's say, a 2n or log n. So I'm going to keep coming back to this, that what should the theory should enable us to do is that it should allow us to predict how the algorithms will perform, and it should allow us to compare algorithms. Between two algorithms, the theory should enable some guidance. So it should have some predictive power, and it should allow us to do comparative power. And hopefully this theory should also allow us to guide how to improve further. Okay?
Can you ever have predictive power without having comparison power?
Not really. I mean, because comparison is just about two algorithms and predicting is about one, but you are right. So if you are able to predict, then you'll be often able to compare. And since this is a theory audience, so hopefully along the way, I'll show that all this work also leads you to encounter some beautiful mathematical patterns. Okay, so how did we come here? Well, Knuth proposed the idea of analysis of algorithms. Edmonds tried to formalize what are efficient algorithms, which is what we call as p-time algorithms. Soon after, we discovered there are algorithms whose answers we can check efficiently, but we can't seem to figure out if there's an efficient way of finding their answers, and that led to this beautiful theory of NP completeness. Cart figured out that not just one problem, there are many problems that are NP complete, and Stockmeyer had an entire polynomial hierarchy based on NP oracles. So in some ways, we now have a very rich theory of algorithms that rely on these oracles. But I would argue that for about 4 decades, this framework that is based on oracle has remained confined just to the theory community. Why so? Well, for a long time, these NP hard problems were really hard to tackle. So we didn't really have a hope of having algorithm that would indeed be calling such oracles in practice. That has all changed now. And for that, we had to thank the development of the set solvers. So what a lot of us in our community call as set revolution. So what's that? You have the canonical NP-complete problem, which is given a Boolean formula, find an assignment that makes the variable equal to 1. So if you have a formula looking like this, then assigning x1 and x2 and x3 to 1 would indeed make the formula satisfiable. These solvers now can solve problems that involve millions of variables. In fact, appealing back to Knuth, he wrote an entire book on set solving. It's all about how to build these solvers, not about the theory. It's all about how to build these solvers. And I think he put it very nicely. These were problems that one thought were hopelessly difficult about a few years ago. The solvers also find applications in all kind of industries as we speak. Some of these companies are running tens of thousands of cores of set solvers, hoping to find bugs in your device drivers or making sure your data on AWS is not corrupted. So this is a real practical tool. So what it also in early 2010s, it kind of became that now that set is easy. And I do want to put easy in quotation. I don't mean to claim that set is easy for every instance out there. Of course, there are formulas with few hundred variables that no set solver can solve. But it is easy for instances that seem to come from practice. So it was time to look beyond satisfiability. And that led to a lot of work on developing algorithmic frameworks for problems beyond satisfiability. So those will be problems in the second level of polynomial hierarchy. optimization, counting, approximate counting that would require polynomially many calls, sampling, synthesis, quantifier elimination. So there's a lot of work that has happened in building these practical algorithm frameworks. So I think now we started asking that, well, now these solvers are indeed really used in Oracle. So here is algorithm which makes calls to the solvers. It's perhaps time to have a theory that's based on this behavior of set solvers. So I keep using the word solver. And we know about a notion that may be very closely related, which is of NP Oracle, right? So, and I'm going to discuss all this focused on Boolean formulas, but what I discuss applies to general languages in NP. So, what is an NP Oracle? So, if you give a Boolean formula, an NP Oracle should return yes if the formula is satisfiable, else no. What does the set solver do? Well, if you give it a formula, and if the formula is satisfiable, it returns a satisfying assignment at no additional cost. Otherwise, it returns no. The modern solvers, when they say no, they also return a proof of unsatisfiability. So they give you a resolution proof why the formula is unsatisfiable. Something else, these solvers also time out.
This is a feature of all solvers?
Yes, the modern solvers, almost all the competitive solvers,
They always give a resolution.
they give a proof that's slightly higher in resolution. So they do have something like, it's not fully Frege, so but they do introduce a extra variable. So there's the existential quantity. And the proof has to be very also in the format more compact. So there's a lot of work. It's called DRAD train. So it gives a proof that some other tool can like unroll it and then check it. So there's a whole machine there. But they give a proof in very compact format.
So, what would these set solvers do if it is given one of these hard but satisfiable things that just run for a very long time? Or?
That's correct. So the solvers will run, but of course, in practice, you will time out.
Okay.
So that's the part I'm kind of going to ignore for now, which is that the solvers time out, but we are right now going to assume that they give a satisfying assignment. Okay. So since we need to, and of course, their behavior for different formulas will be, the time it takes will be different. Yeah.
So, guessing like, suppose you've designed a system and you're checking if the design conditions have been met. So that's a proof, right?
Yes.
So such a formula would be unsatisfied.
That's very right. So often,
So then the proof will be the formula is unsatisfiable, so your theorem is correct.
yes.
So if you have a bug, it will time.
Not really. It will. I mean, it can time out even if the formula is unsatisfiable. So at the timeout, sorry, can happen on both satisfiable or unsatisfiable.
Both.
No, but in the other case, it is bound to happen, right?
No, neither case. I mean, you are just searching for a proof or searching for a satisfying assignment is the same thing.
But I mean, sorry, I'm just blanking out
Yeah.
here. Because suppose the theorem prover is assumed it to be a theorem, so looking for the empty clause and not unable to derive it.
Yeah.
It is able to understand that there is no that this formula is actually satisfied.
No, so that's very something important. So the moment it knows that it is satisfiable, it also has a satisfying assignment. So without having a satisfying assignment,
It will never understand. that
yeah,
there is-
it will. So without either it has a satisfying assignment or it has a proof. Without it, it cannot infer. And that is something that
You can potentially time out in both these situations.
it can time out in both the situations. And that's something I do want to emphasize more, that the solvers will, when they terminate with yes, they do have a satisfying assignment. The way these solvers are implemented, they have no way of figuring out the formula is satisfiable without having the satisfying assignment in hand. And this is an observation that I want to argue is not just limited to set solver. This is the observation for what I would call as any tool that you can download and run. for combinatorial problems, the same remains. So if it's a ILP solver, IP, mixed into the linear programming solver, all of these, when they say that the set of constraints is satisfiable, they know this witness. So which also means that they don't pay any additional cost to give a witness. It just comes for free. If you know the formula is satisfiable, you have the witness. So when we are trying to model the behavior, because we don't want to deal with the pesky issue of the time, so we are going to say, well, the solver is going to return the satisfying assignment, and I'm also going to ignore the fact that they return the proof. This is something I'll come at the end of the talk. So right now we'll say it returns a satisfying assignment, else it returns no.
Why is this different from an NP oracle?
That's a good point. I mean, in case of NP oracle, if you look at it, it just returns yes.
Yeah, but you can remove variables one by one and get
Exactly. So at this point, it's right to ask that, hey, is this not something we teach in undergraduate, that if you have an NP oracle, you can get a satisfying assignment one bit by one, right? Well, how long does it take you to find a satisfying assignment using an NP oracle? N calls. How long does it take to find a satisfying assignment with a set oracle? One call. You might say, well, this is just a difference of n. I would argue that this is the difference between the solvers from 90s and the solvers today. If these solvers were factor million times slower, Knuth won't be writing a book, these companies won't be using this, there won't be many tools out there. This is the factor that we care about. Factor of n truly matters. You might say, well, for every problem, maybe it is the case that for every problem you find the complexity in NP oracle and the complex in the set oracle will be just off by a factor of n. Not really. I mean, if the just for the set of rhetoric argument, if I just want to know if the formula is satisfiable, it costs you have to make one call to the NP oracle and one call to the set oracle. So there are problems where the complexity of NP versus the set oracle, as the model I propose here, is off by n, and there are problems where they both have the same complexity. So we can't just simply ignore that the complexity will be off by n, because we do care when the complexity is 1 versus n. So I think this is where we had to do the fine-grained analysis for all the problems out there.
Then maybe I missed it. But
Yeah.
do we have NP oracles that are any faster than SAT oracles? Or do
That's a good point. We don't, I mean, NP Oracle was a model proposed to look in future, that if one day we happen to solve, that's not what we have. What we really have ended up with are set solvers, which are the physical objects.
Right.
And the argument is that we have this NP Oracle theory built for something which is not what the physical object behaves like. So now we have this physical object, so it's important to come up with the right model to analyze the behavior of this physical object. So hoping that we just apply the NP oracle theory as I'm talking about here isn't the right way to analyze the behavior of when we implement the algorithm.
So you're saying like even for, not from theory point of view, but just from practice. So there are no interesting algorithms, heuristics, let's say, that if they wanted to all to do is to implement an NP oracle,
Yeah.
would have an advantage
Yes.
in terms of running.
Yes. And I'm arguing that this is just not even limited to the Boolean formula. For any combinatorial problem,
No, I understand. So you're
Yes.
saying that there are none that is no.
there are none that is not.
You just end up
Yeah.
finding.
So none that is non in the sense like you can download and run it.
Yeah.
Yeah. All right. So As I mentioned, well, we had to figure out for what problem there is what's the difference. Maybe for some problem there is a factor of n difference. Maybe for some problems the factor is less than n. And we do need to analyze for what problems what's the complexity in the set oracle model. And the subtitle of the talk was really like, what is the power you get from getting a satisfying assignment? And hopefully by the end of the talk, I'll convince you that we should really try to develop a theory for oracles that can capture the physical reality out there, which is that the set solvers and combinatorial solvers are a reality out there. So we do need a theory that can capture their behavior. In this talk, I'll talk about two problems. One is sampling. So the problem is you are given a formula and we want to sample solutions uniformly at random. We do allow some tolerance. So we would like every solution to be sampled within 1 plus epsilon factor of the ideal uniform property. In case of approximate model counting, we have a formula. We are interested in counting the number of solutions of the formula. We allow two more parameters, epsilon and delta. We compute the count, which is within 1 plus epsilon factor with confidence at least 1 minus delta. Throughout the talk, I'm going to assume epsilon and also delta to be a constant. Okay. So I'll start with one of the reasons to choose these two problems is that there's a deep relationship between these two problems. In particular, the seminal work of Jerome Valent and Vazirani showed that these are interreducible. So what does it mean? Given access to a counter, I can implement a sampler. So let me tell you how that algorithm looks like. So an approximate model counter from the classical result of Stockmire can be implemented by log n times log 1 by delta NP calls. Okay. So how do we do a sampling? How do we sample solutions uniformly at random? Well, that is kind of very simple. So we have to figure out whether to assign x1 to 0 or 1. So we should assign x1 to 1 with the probability, the number of solutions where x1 is 1 over all the solutions. Once we assign, let's say, x1 to 1, we have to now decide what to do about x2. So we should assign x2 to 1 with the probability, the number of solutions where both x1 and x2 are 1 divided by the number of solutions where x1 is 1. And so on until we assign all the variables. Turns out that from the complexity analysis, each of the calls to these counters had to be made with delta, that is 1 over 2 to that. So the delta has to be really small. So this is the algorithm. Let's try to analyze its complexity.
Can you show me what is delta again?
Delta is the probability.
So why do you need to be exponentially small? Why not 1 over n?
So the thing is that when you are doing this analysis, you have to take care of all the counts that you get. So that requires it to be 1 by 2 to the n.
You only get n counts.
There is maybe like we take it all. I mean, this is
I mean, the right analysis
Yes.
need to be right
on all the points. So you do
and the chance that, I mean, your confidence naively looks like 1 minus delta to the n because you have n different sequential calls.
Yeah, but if delta is 1 over n, then 1 minus delta is a constant.
So the thing is that you want to ensure that the probability is correct for all the. I mean, we are looking at the uniform distribution for all the points. You don't know a priori what queries you are going to make, so you have to do a union bound on all possible events. It's small. Yeah, we can. I mean, not the focus of the talk, known for a long time. So,
Kuldeep?
yes.
So, solution of findings or the number of satisfying assignments.
Yes. Sorry. Yes.
So, how do you know this probability beforehand?
Oh, we don't know this probability. We had to count the number of solutions, and this is where we can invoke a approximate counter. Yes, absolutely. We don't know this, right? So we had to call an approximate count. All right. So how many calls we are making to the NP oracle here? Well, we are making n calls to the counter. Each of the call we are setting delta to be 1 over 2 to the n. And each of the calls we are going to make. Yes, so how many calls we end up making? We end up making, yes, delta is 1 by 2 to the n, so n square log n calls. How many calls we are making to the set oracle? Well, no difference really. We are just invoking the approximate model counter. So we make n square log n calls. So this is kind of an algorithm that doesn't really use the power of set oracle.
What is hence?
Oh, because the delta is set to be 1 by 2 to the n.
You make n,
So-
there are n calls.
So this is an algorithm that isn't really using the power of set oracle. But at this point, you can ask, like, can you think of an algorithm that would be better because you had free access to satisfying assignment? Can you come up with an algorithm with better complexity? And that's where we answer yes. You can have an algorithm with better complexity with respect to set oracle. So what does that algorithm look like? Well, the high level idea is that you have a space of all possible assignments. The dots are satisfying assignments, so we can partition the solution space into small cells. We go and pick a random cell. We enumerate solutions in a randomly chosen cell. Go and pick a solution uniformly at random.
Sorry, how do you make the cells?
Yes. So how do we partition? So that's one challenge you need to encounter, which is that how do you partition into roughly equal small cells? And this is where you rely on this classical idea of three-wise independent hash functions. Again, for technical reasons, you need three-wise because you condition on a solution so for things to go through. You can't do it with two-wise.
So, just to go to the previous picture.
Yeah.
So the idea is that we want to partition into cells such that each cell roughly contains the same number of satisfying
Yes.
cells.
Yeah.
I see. And this is going to be done by just looking at, conditioning on the output of some three-wise independent hash
Yes.
function.
Yeah.
Right.
And in practice, this can be implemented by using XORs. Because three-wise independent hash functions, you can encode these as XORs, which of course relies on some work to make them work with the set solver. So there's a whole line of work in making it practical. And how many cells do we have to partition into? Well, we want all the cells to have about threshold many solutions. If epsilon is constant, threshold turns out to be 200. Then we can figure out how many solutions there are by making one call to approximate count. Okay, so the entire algorithm is make a call to approximate counter, figure out how many cells to partition into those many cells, pick a random cell, enumerate the solutions, pick a solution uniform method.
So why are we enumerating solutions at all? Can't we just, run the stat solver with the, the cell being, basically modify the formula that basically says I want this formula to be true and the hash value must be blah. And can I just give this to the stat solver? Right?
But you still have many solutions, so you have to
It will
choose.
give me one uniform.
Yes. We can't imagine the solver will give us, but otherwise we could have just run the solver
Right at the beginning.
at the beginning.
Oh, sure.
Yeah, so of course we can't. All right, so this is the complexity analysis. So what did we do? We made one call to the counter, followed by enumerated threshold many solutions. Threshold is a constant. So one call to the counter costs log n. Enumerating solutions, constant many solutions with the NP oracle costs n. From a set oracle perspective, log n calls to for the counter plus 1 plus constant plus 200. So we did indeed get a better algorithm if you start thinking that you get satisfying assignments for free. Let's analyze these algorithms. The earlier algorithm had the complexity of n square log n. The new algorithm in the NP oracle has a complexity of n plus log n. In the set oracle, it has a complexity of log n. Well, at this point, you can say, sure, you can come up with another model, get an algorithm with a different complexity. The real power of these oracle models would be if they can predict what will happen if we were to implement these algorithms.
Why is it just login for a SAT oracle?
Because you make one call to the counter, enumeration costs, you are enumerating a threshold many, constant many solutions.
But yeah, how do you enumerate that?
Oh, the way you enumerate, you find a solution, you say, not this one, give me something else.
Oh, I see. So now you're restricting yourself to a situation where there are only 200 solutions, so you just do this.
Yeah.
Oh,
Exactly.
yes.
By writing it again as a stack.
Yes.
Ah,
Yeah.
oh.
And in fact, all the solvers give this nice API. You can ask them to enumerate. But you can also write your own, the side close, not this one. All right, so think about, we had these algorithms and we had two oracle models to analyze their complexity. So suppose NP oracle was the right model to analyze the complexities. So if you were to implement these algorithms, what do you think the behavior will be? It will be a behavior between a quadratic algorithm versus a linear algorithm. Right? You have a quadratic algorithm and the other algorithm is linear. Suppose the set oracle was the right model to analyze the complexity. The behavior would be between a quadratic algorithm.
Algorithm is still linear because you are constructing this clause, right? It's only the number of calls that has gone now.
Yes.
The algorithm still has a factor of n.
Oh, so
even assuming that oracle call is order 1.
So I think something I should emphasize. So in all these algorithms, everything else you do is just have very. Remember Knut's model about.
Only scaling we are looking at is the number of calls.
Yes, remember Knut's model about operation cost. So everything else is a very small cost. So you can ignore that part and only the calls that determine. All the time you spend are just the calls. Okay, over 99.99%. Everything else is writing, not even on disk, on the memory. So we would be between a quadratic versus linear versus a quadratic versus logarithmic, right? So we went about and implemented these algorithms. And here's how they behave. These are different benchmarks. These are the number of variables in each formula. These are the number of clauses. This one kinds of times out on everything except the tiniest of the formulas. This one scales. When you look at a quadratic versus linear algorithm, you don't versus quadratic versus, if you look at exponential gap versus a factor n gap, you should be able to see how the plots would be. And this is my strongest argument why we should do analysis with respect to set oracle. Because that would allow us to predict what would happen if we were to implement these algorithms.
So just out of curiosity, when you say timeout, what is the?
We had 3600 seconds as timeout. But some of these, even if you had larger time, I suspect it would time. But the experiments were 3600 seconds. 1 hour.
Do you see logarithmic dependence in this?
So something else I do want to point out. One thing that we were abstracting away was the time taken by different calls. So it is indeed not the case that the formula with a large number of variables takes different formulas take different amount of time. So the calls is of course logarithmic, but each of the calls, the model that we abstracted away by saying all the calls are about the same, that's where you see the variation. And that's indeed the weakness of the current model. It's not able to capture the behavior for different formulas.
Why can't we just count the number of calls?
Because not every call takes about the same time.
But that shouldn't matter for you, right? I mean, you're just interested in the number of calls.
Yes, from the complexity perspective. But if you truly want it to be predictive, then we would also want to understand. I mean, the real goal of algorithm analysis is that you give me a number and I'll be able to see what would happen if I were to implement it. And that still fails here, right? Like these two formulas, what explains that this takes 3,300 seconds and this one takes 5 seconds?
So benchmark is like, what is the benchmark? It's a set of.
It's a one formula.
One form.
Yes. Okay.
How is this sorted by, I mean, like, I initially thought it was variables, but no,
Yes,
it's not.
no, it should be variables. Okay, maybe I missed one of those.
But
Yeah.
clauses also, it's not true.
No, I think it should be variables. So it's just like some one or two I missed.
Okay.
And you identified exactly the line I missed.
No, I was wondering if there is some reason in which this.
No, it should be just the variables.
Okay.
Yeah.
Formula, 17 variables.
So it's a family of form.
No,
No.
It's one formula.
Each of them is
One formula. This many variables with this many clauses.
yes. We of course have experiments on some 1,000 benchmarks. I'm just showing some of them.
You just pick variables.
All right, so that's talking about sampling. Something I do want to highlight is that because now you think that, oh, I am in this model where getting a satisfying assignment doesn't have a high cost. So I can get, let me try to design algorithms that can exploit this power.
By the way, so where these formulas come?
Oh, this problem matters to people in practice. So there are lots of benchmarks that come from EDA industry. Yeah. And this model also allowed us to develop a new algorithm that solely relied on the idea that enumerating satisfying assignments or getting satisfying assignment doesn't cost. Let me talk about another problem, that is of counting. So again, we are interested in a count that's within 1 plus epsilon factor with 1 minus delta confidence. And this is of course NP hard. So Stockmeyer had this brilliant insight. I was like, okay, how are we going to ever develop an algorithm for this problem? So this is NP hard, we don't know. So we had to abstract away NP queries to the NP oracle. But we also need an interface to make queries to NP oracle. So Stockmeyer's idea was that, look, the counter is going to send a formula psi. So if we are interested in counting the number of models or solutions of phi, but counter is allowed to send some formula psi, and the oracle will tell us whether phi and psi is satisfiable or not. And the counter is allowed to have these queries to be adapted. So it can decide based on the answer what should be the next psi. It's an amazing fact that Stockmeyer could really envision how these algorithms would actually be developed, because the current approximate counting tools, all of them fit this Stockmeyer's model broadly. They send these formulas, you get them, and you make these queries to be adapted. There's a lot of work in how to figure out these queries and so on. But all of the queries are indeed of this form, phi and psi. So this is kind of as good as you expect from a model that can predict next 40 years. And Stockmeyer also gave a lower and upper bound on the number of NP oracle calls. So the idea for the lower bound, if for a minute, if you discount the fact that this randomized algorithm, if it was this deterministic algorithm, then let's say we are giving a constant factor approximation, a factor 2 approximation. So we have n possible answers. Every time we are going to make a query, we'll give an answer yes or no. Well, for this decision tree, this looks like a decision tree. For us to be able to give n calls, we better have a log n depth. So that was a necessary argument. Then you just use Yao's lemma to argue this also holds for randomization. All right, so that's Stockmeyer said then log n calls are necessary, And in his work, he also showed why they also came up with an algorithm where they were sufficient. It did turn out that the Stockmeyer's upper bound did not really lend itself to practical methods. So the upper bound algorithm is highly impressive. So along with lots of collaborators, I spent about 13 years trying to develop an approximate counter. And as I mentioned that we always wanted to analyze the complexity of this, and there was a very pesky issue. So if you look at the complexity of this algorithm from NP Oracle model, the complexity is n log n. From the set Oracle model, the complexity is log n. Where is this factor of n coming in? Because we are again making these kind of queries. Is the number of solutions less than threshold? Of course, in case of NP Oracle, you had to pay n times the threshold. In case of set Oracle, it's threshold. There are some ways of reconciling when you end up in a situation like this. You can say, well, there is theory, there is practice. So maybe in theory, an algorithm with complexity n log n that works way better than another algorithm whose complexity is log n. And such is life. Or maybe we should look at the complexity from a different model, which is the set oracle. In that case, look, these two algorithms still have the same log n complexity. It doesn't still say that why one is better than the other, but it's a little bit more digestible statement. It's also, I want to emphasize that if you were not trying to look at the complexity from the set oracle, you wouldn't want to come up with an algorithm with n log n complexity. Right? You already have log n. The best way to improve algorithms is not to increase their complexity. So as I mentioned that this Stockmeyer's model does capture the algorithms, but it doesn't fully capture the current implementations. Why so? Because we implement using set solvers. And as a set solver, when the formula is satisfiable, they actually return the satisfying assignment. So a natural extension to the Stockmeyer model is to replace NP Oracle with set Oracle, because that kind of captures what's going on here. So every time you make these queries, you get a satisfying assignment or unset. Now that we have a new model, we can ask these questions again. Well, how many queries are necessary? Look, if you have upper bound for NP Oracle, that also carries over the upper bound for set Oracle. But so it's not true for the lower bounds. The question also has origin beyond curiosity, because we were getting satisfying assignment for almost a decade and we did not know what to do about this satisfying assignment. So here algorithm, if we could figure out what to do about it, we would do to gain some advantage. So does having satisfying assignment give you more power for approximate model counter? And unfortunately, turns out the answer is no, up to this polylog factors. So we showed that every counter must make log n queries to set on it.
So here, I mean, so here you said that even if the formula is unsatisfied, you get some proof of unsatisfied.
Yeah, so we are ignoring that part.
You are ignoring it.
Yes, agree. Yeah. Okay, so in case of set oracle, why so something I want to highlight. This is where things become very interesting from technical perspective, because the lower bounds don't carry over, and the reason is you get much more information. So if you just wanted the same decision tree argument, then when the formula is satisfiable, you can get any of the satisfying assignments, and the same argument doesn't go through because you can have exponentially many, so you get something very trivial, even worse than trivial log n by n. So, And this is something I want to highlight, that the decision tree based arguments are common in these NP Oracle models because you get yes and no answer. So if you want to analyze problems from the set Oracle perspective, you'll get these technical difficulty immediately. So how do we go about analyzing? Well, there is one issue about the set Oracle, which is that which satisfying assignment is it going to return? So maybe it can be cooperative or it could be adversarial. So we consider the model where it returns as satisfying assignment uniformly chosen. So among this space, it doesn't favor any of them. I'll have a quick sketch about how these proofs go through. I got to know that Gunjan couldn't give the talk, but this is what he developed in his postdoc. So he had an entire talk ready to tell you how he went on to analyze these things. So I'll just give a quick sketch. Thankfully, I didn't put in the slide that Gunjan's talk from yesterday. So, okay, so how do we go about this? So let me sketch just to give some ideas, and I think why it required different style of techniques to do that. So a general counter gives you give a formula, it gives back a satisfying assignment. We want to come up with some restricted model. So we call a restricted model where instead of getting a satisfying assignment, all it gets to know is if the satisfying assignment was equal to any of the previous satisfying assignments. Incredibly limiting if you think about it, right? So all it gets to know is that if this satisfying assignment was same as any of the previous satisfying assignments. Of course, all it needs to know which one, because so far we already figured out which ones are equal to what. So you have just 2 into I minus 1 possibilities. So if you think about like these are the kind of queries we are making, psi1, psi2, psi3, psi4. Let's say the set solver in practice, the set oracle finds assignment sigma 1, sigma 2. So we'll get to know they are equal. We'll get to know sigma 3 is some assignment, sigma 4 is some other assignment. If that's the only extent of information that is being revealed. So the degree now we can bound by 2i. So if you are making q queries, then 2q. So that allows us to get the lower bound to square root log n. Now kind of making this formal, essentially making usage of the Fenner's inequality, we can improve the bound from square root log n to log n. But this is for this very restricted counter that just gets to see this information. Of course, the hard work goes in to argue that this counter can simulate a general counter. This restricted model is as powerful as the general counter. So the general counter also must make log n queries. And why does that go through? Well, if you think about it, consider 2 counters that I made these so far. All the queries, we are going to keep their transcripts. So they make a query, they get a satisfying assignment. And let's say these 2 counters end up with the same, they had a different history, but the same configuration. Then you have to argue that they haven't gained much information about the formula solution space. So you construct these formulas with among this space with different counts. And this counter must not have gotten much information about which of the counts the formula lies. So essentially, you can always do this. Given this information, you can always do this relabeling where the formula isn't getting much information about the counter isn't getting much information about which of the bucket the formula lies. It's kind of the most hand-wavy argument I can give you. And that allowed us to show that you do need log n queries to the set for approximate count.
Where do you use that, when the assignment is uniformly randomly chosen
So that we had to use,
for this?
yes, I think when you are doing this panel inequality, that's where. We also do have some cases where, so the hard case that we constructed over the uniform space of the formulas, the hard case can still have information encoded by the satisfying assignment. The hard case that we have, where you could say that, oh, if this satisfying assignment is here, then I know like which bucket the formula belongs to. So in order for us not to reveal that, it would be nice if one can remove this. So this is what we have right now. It would also be interesting to, although that's not how the set solvers behave, but perhaps from theory perspective, how adversarial the. But that's, I guess, since we know the upper bound already, that the upper bound does not assume anything about the behavior of solution formula. So we know that you can always do with log n. So being adversarial isn't going to cost you. Being cooperative can help you, but we don't know how to formulate that.
Let me ask over here. So in the sense as the equivalence you showed that this oblivious, semi-oblivious is the same as
Yeah.
this. Would that be violated if you had these
Yes.
counterexample, if you have these unset proofs, that would be violated?
Oh, no. Unset proof, we don't know.
You're not sure. Okay.
Yeah, no. Somehow, yeah, that we don't know.
So in the sense that using the fact the SAT oracle also gives an unset proof when it's no.
Yeah.
Okay.
So I'll come back to unset proof just in 2 slides. That is much more exciting. But we don't know right now because when all the algorithms seem to only like unset just tells like you have put too many XORs or too many. Somehow we don't know what to do. Yeah. So to summarize this part on approximate counting, 2 things I want to highlight. One, we have this. It somehow allowed us to reconcile the situation where you have practically efficient algorithm that seem to have really bad complexity in the classical model. But now at least the 2 algorithms have the same complexity. And it also helped us, in some ways, it was consoling to know that there's no obvious way to use the power of satisfying assignment. So all these techniques that would get the satisfying assignment, we did not know what to do about it, and it looks like there's no obvious way to use the satisfying assignment. So if you don't assume anything about the behavior of the solver, then there is no way to use the power of satisfying assignment. And of course, the other thing that I want to tell you is that most of the lower bounds in the NP oracle model are based on this decision tree argument. And that just does not carry over in the set oracle. Because you don't get yes or no, you get much more information. So it would indeed be nice to tackle any such problems because this is the immediate technical barrier one hits. So to summarize, we want a theory that should allow us to predict the performance, allow us to compare algorithms, and help us improve those. And along the way, hopefully, you get interesting technical challenges. In case of sampling, we saw that the set oracle does capture the algorithm performance. It also allowed us to develop it enabled us to develop new algorithm because you start thinking, oh, I'm not paying additional costs, so maybe let me think through this idea. In case of counting, this allows us to reconcile the current state of art. And, we see that there are new technical challenges. The existing ones don't work for the set oracle model, especially based on the decision tree. So where do we go from here? Well, I do want to emphasize that we have barely started. We have looked at 2 problems. The entire polynomial hierarchy here to be explored with respect to different oracles. Okay. Let me talk about one problem that I think is very ripe to be explored, which is max set. So what is the problem of max set? You give me a formula which is unsatisfiable. So the simplest version of max set is to tell me how many clauses can be satisfied. What's the maximum number of clauses that can be satisfied? Again, for max set, log n calls to NP oracle are both necessary and sufficient. The necessary argument again goes through the decision tree. You have an answer, one of the answer, you must be able to have a log n tag. And similarly, you do the sufficient argument. But what about set oracle? And I want to emphasize that that's just not for mere curiosity, because we actually have max set solvers out there. And these max set solvers call the underlying set solvers. And these max set solvers, if we could have figured out that there is some way we could use the satisfying assignment, that can lead to practical improvements. So if it is possible that in case of max set, getting satisfying assignment is powerful, it can really lead to practical benefits. Something I do want to emphasize, these max set solvers. In last 10 years, a lot of algorithmic improvements came from the idea of using the proofs. So what the solver returns the proof, how do you use it intelligently? And there's a new, completely different design of max set solver that was solely enabled by trying to exploit the proofs. So this is the approach based on the hitting sets. So this was solely enabled, one, by the development that the set solver started providing the proof, and second, this algorithmic idea that could use the proof. So these solvers really go beyond the answer yes or no anyway. What we don't know right now, anytime it returns satisfying assignment, we don't seem to use it more than we know, like, okay, this is satisfiable, so we have to figure something out. I usually satisfying assignment say that, oh, you could perhaps go more. Beyond that, it would be interesting to find relationship between the problem that can be solved by one query to set oracle versus log n query to set oracle versus n queries to set oracle. We don't know answers to any of these. We don't know what's the relative power between these different classes. And finally, I've been talking about set solvers also provide proofs. And how do we incorporate proofs in the Oracle model and argue about the power of proofs? So there is a lot to do. We have barely started. So I hope some of this gets you excited about. And along the way, if we build this theory, it will at least try to capture some bit of physical reality. So with that, I'll conclude. I'll be happy to take any questions.
Question?
Yeah.
Yeah.
Kuldeep, so from a practical perspective, why did you talk about ILP solvers and why were you talking about SAT solvers? Is there something?
No, it's just like what I focus on.
Okay.
Yeah, but something I do want to emphasize that ILP solvers also always give a satisfying assignment. The state of about the proof is perhaps not as advanced as in case of set solving.
But in terms of scalability and things like that?
Oh, yeah, so this is kind of something, there are lots of workshops between the two communities where we try to understand. So there are problems where, ILP solvers will be way better than set solvers. Kind of this packing problems and scheduling problems. And then there are problems that are, in the EDA, in electronic design automation, where the set solvers will be way better. Of course, one can translate one from the other. The encoding doesn't blow up, so it's not any of the issues about encoding and all. It's just the different heuristics seem to do better for, so that's of course an interesting problem on its own. Proofs have developed much more in the set community, partly because it's also it turned out from very fruitful work that originated in the theory community, which the idea about capturing the behavior of the solvers from the proof system on which it's operating. And it turned out that this conflict-driven closed learning with restarts can simulate resolution, and that was a very fruitful observation that allowed you to kind of say, okay, we should be able to come up with a proper proof. So developers wanted to always have some trace to figure out why we return unset, but it wasn't really clear how to go about it until about 15 years ago. And now there's a lot of work in the proofs.
So in this sort of fine-grained level, it might, these differences might also matter. Do they matter, for example, if you replace SAT by some other NP-complete problem, like for instance, if it was, I don't know, something like three-colorability or any other thing. There again, there is this thing of decision versus search as being your oracle. Your oracle just telling you yes, no, versus the oracle giving you some notion of a greatness.
Yes, so it may matter because if the encoding from one to the other blows up, then you might care about it. Yes. That's.
But any models have all.
No, I'm just saying that, I don't know, but isn't it true that everything is converted into a SAT form?
Yeah, but that the blow up is basically where this extra factor of
No,
N
the existing solvers, they're all.
Oh, sure. Yeah. No, the solvers are built keeping SAT in mind because in some sense that's the most natural.
No. Also, something else I want to. So that's so this maybe we don't call it SAT oracle, but maybe search oracle. So in the idea that given the problem language in NP, you get a witness. So that we can go with that model without having to say that it must be a Boolean formula. So that's an observation that is consistent across for other, whatever languages that you want to deal with, like whether it is the Boolean formulas or constraint satisfaction problems, ILP, in each of those, in their own communities, they do the same thing in the sense like you always get a satisfying assignment. So I think maybe the model can be lifted to not to the Boolean formulas, but at the level of language, then it should not be.
I was just curious, for example, if you give one of these SAT solvers a particular formula and ask it to compute the lexicographically larger SAT assignment or something, do they do well? Do they perform?
Yeah. So that's a good. Those are all different variants of maxset, but we know like Lex maxset is complete for FP to NP with N calls.
Yeah.
And you do see the difference between Lex maxset is indeed hard in practice for the maxset solvers than a typical maxset. So you do see these broad strokes of complexity also appear in implementations.
So does all this NP, approximate conflict, everything may not be capturable in P2 SAT?
No.
But this lexicographic thing is just another SAT form, right? It's just about twice the size.
No. So computing the max largest SAT assignment is a complete problem for P to the SAT. And it's one of these problems that actually requires N calls to the oracle.
Yes.
So they're missing
P to NP with N. We don't know for SAT.
Oh, sorry. Yes. P to the
So it would be nice to understand for each of these what's the case when you get a satisfied assignment.
But why is the lexicographic SAT not math SAT? Isn't this SAT a SAT thing? You say the formula, then say for every other solution. So phi of x and phi of y implies y isn't.
No, but how will you write for all in the?
No. Phi of x and for all. So it doesn't get phi of x. Oh, there's a for all thing.
Yes.
So that's not there exists.
Yeah. That is indeed, yeah. But also you see in practice also this, because you can encode with this kind of bit vector, like exponential weights. You can say the first bit, and then it's kind of funny in the sense the solvers don't get so affected by the weights, but somehow the performance still differs.
So because this is, usually when I teach complexity, one of the things that I try to stress is the fact that if you look at NP to the NP, you can get away with a single query. But somehow for P to the NP, you can't. And this Lex largest SAT assignment is the sort of canonical example to sort of say that something very weird.
Yeah.
Yeah.
But for all of these, I think.
But now, if you get more information, I don't know what happens.
Yes, so that's the point. But you get all the information. There are no NP oracles that that capture any physical object out there, right? Only set solver that work.
More information is like.
You get
The
you get the satisfying assignment if it's satisfiable, or you get a proof.
Yeah.
Well, so like, in practice, everything is converted into stat, but perhaps depending on the domain where it's coming from, there will be domain specific structure, right? As have people studied looking into.
Oh, yes. That's why not everything is converted to set. For example, if it's a scheduling or packing problem, and these ILP solvers are way better at it. So, if it's or constraint programming solvers, so somehow problem that come from train scheduling, these solvers are way better at it. So the high level design between all these solvers, I mean, not for all the ILP solvers, but like constraint programming, CP and set is similar. You are doing some search, some learning, some backtracking, but I mean, devil is in all the details. And somehow some problems are better for one set of heuristics versus the other.
But there are like explanations for that, or why are
We have some explanations. So there is this like long running theory and practice of set solving workshops that so we have some ideas about, but the state of art right now in our explanations is that we can indeed come up with formulas where these solvers will take exponential time and not just nasty like pigeonhole kind of, you can come up with something more. And there the argument is that usually these are unsatisfiable, I mean, not usually, almost always these are unsatisfiable formulas, because there you argue that, look, the resolution proof that you are going to get is going to be large side. So no matter what your solver is doing, it has to. Some solvers do slightly more powerful proof system than resolution, but even for those, you can argue that the proof is going to be large. Where we struggle a lot is figuring out when the formula is satisfiable. Because why should it take a long time? Why did it not know that it should just assign this variable this and that variable that? So yeah, that's kind of the. So there's a lot of work in trying to understand the performance. This work is more about the behavior, which is that it returns the satisfying assignment.
There are sort of two heuristics being run in parallel when you given a formula like.
Oh no, this book is very big. There are thousands of lines of code, lots of very. So I mean, high level heuristic is very simple. Figure out a variable, assign it. Then figure out what do you get after this assignment. Looks like if you can infer that this is not going to land you to satisfying assignment, backtrack. So when I tell you, it looks like you are always looking for a satisfying assignment, but the backtrack is always figuring out these resolution steps. So in some sense, you are looking for a proof of unsatisfiability. And in the solver, as it is trying to find the proof of unsatisfiability, sometimes it fails, finds a satisfying assignment.
No,
That's-
this is the part that I'm
Yeah.
process of trying to build a proof.
Just do this offline.
Yeah. So maybe, yeah.
That's not the offline was already done.
Yeah.
So here doors planning.
Uh-huh.
That including.
Okay, let's just thank Kuldeep once again.
Thank you.
No, I will think.
Yeah.
So, I mean, you're saying it's somehow mimicking the resolution.
It is, yeah. So I mean, yeah, there is like very nice set of questions here. So what we know is that